In this first lecture on quantum mechanics, today we shall try to arrive at Schrodinger equation. Let me start with the Berkeley hypothesis. As per the Berkeley hypothesis, every material particle is associated with a wave called the de Broglie wave. The wavelength of the de Broglie wave is given by lambda is equal to h upon p, where p is the momentum of the particle. It is found that for microscopic particle, lambda is appreciable and can be measured or felt with the present day available instruments. And for macroscopic particle, lambda is too small to be detected by even with the most sophisticated experiment that are with our hand. So the quantum effect is not felt for macroscopic bodies. This expression for wavelength has been experimentally verified by Davison-Germer and G.P. Thomson experiment, and ultimately we believe that this expression is correct. Now the next point is how to represent a de Broglie wave associated with the material particle. We know that it is the wave packet, that is the superposition of a large number of simple harmonic waves with varying frequency and amplitude can represent a wave packet, which is simply given by this e to the power I in one dimension kx omega t integrated over k over all k. This gives you the desired wave. As for example, if we what is the characteristic of the de Broglie wave? The de Broglie wave which should have a large amplitude right on the top of the particle and zero elsewhere. Furthermore, the width of the wave must be comparable with the physical dimension of a particle. So that is, for a particle with small particle, the wave will have smaller will have small width, and for a larger particle, the wave will have a larger width. And another thing is that as the particle moves, the wave as a whole must move with the same velocity, that is with the particle velocity. That is to say, the group velocity of the wave packet must be equal to the particle velocity. We know that the wave packet satisfies all these properties. So we come to the belief that a wave packet can represent the de Broglie wave associated with a material particle in an adequate fashion. Now the problem is that how to get an expression for this wave packet or wave function that we call. If we consider a wave in classical physics, say an elastic wave, the equation for the elastic wave is derived from the by using the property of the medium through which it passes, and for the electromagnetic wave it is the Maxwell's equation with Maxwell's modification of Ampere's circuital law, which leads to the equation. But here there is no such physical principle which can be utilized to find out a differential equation satisfied by the wave packet or the wave function. First question is that why we are after getting a differential equation, not anything else. Basically, let me first answer this question. Basically, we are interested in exploring the dynamics related to a macroscopic particle. So by dynamics we mean the particle, say, initially was at x and t, where I am considering first one-dimensional case, and now the particle is moved from here to a neighboring point x plus delta x and t. What will be the behavior over there? This is given by the del x. If we now come to this point where x kept fixed and t has been translated from t to t plus delta t, what will be the behavior over here is given by the partial derivative with respect to t. And if we want to come here, that what is the quantity is related to the dynamical system at this, then in coming there we need del x, some combination of del x and del t. That is why we are interested, or the physicists are interested in having a differential equation to describe a dynamical system. So the first aim is that we want to find out a differential equation that will be obeyed by the wave packet. Another requirement of the differential equation, if it can be obtained at all, that this differential equation must be a linear one. The linearity is required from the fact that if we have a linear differential equation and whose solutions are y1, y2, y3, then c1, y1, c2, y2, c3, y3 is also a solution. That is, the superposition principle is applicable. In quantum mechanics, superposition principle is very important and must be accommodated within the theory. So the differential equation that we are looking after must be linear. Since there is no clue how to get the equation, we start with a very trivial problem. A very trivial problem means a free particle in 1D, a free particle in 1D. By a free particle we mean that the particle can move along x-axis from plus infinity to minus infinity, and it is possible to have particle everywhere. That is to say, if we speak in terms of probability, which has been included in the quantum theory, that it is equally likely that the particle will be obtained everywhere on the x-axis. That is, we must have a wave which doesn't have any attenuation in respect to space and time. The only wave that we know which is unattenuated in space and time is a function of this sort, the plane wave. So to start with, we assume this is the wave packet. We assume this to be the wave packet. For 1D free particle. Now what shall we do with this wave function? We know that we are looking after the partial differential equation involving space and time variables. So aimlessly, we try to differentiate this. We get ik and psi vac. Now we know the momentum is given by h cross k. Momentum is given by h cross lambda, h by lambda, which we write h upon 2 pi into 2 pi by lambda. This h by 2 pi is called reduced Planck's constant, h cut, and this is k, so this is h cross k. So we are very near to having p. So what we do, we multiply both the sides by minus ih cross, so that this is minus ih cross, and I square is minus 1, so this is plus 1 plus h cross k psi, or it is p psi. We call this look at this equation like this. This is something p operator operates on some function psi, gives you back the p times psi, where p operator is defined as minus ih cross del x. Similarly, if we differentiate this expression with respect to time, so here we have come by del x operation, and if we come by del t operation, we come to del psi del t minus I omega and psi back. Again we multiply it by IH cross, and then we will have IH cross. So this is plus H cross omega psi, or this is E psi. So we write E operator operating on psi gives you back energy value times psi, where E operator is defined as plus IH cross del T. Now we seem to have seen some light amidst the dark. That is, we can consider that the dynamical variables P, energy, momentum, energy, position, the dynamical variable can now be looked upon as operator, where the operator corresponding to position, momentum and energy has already been obtained, and only thing is to obtain the operator corresponding to position, which would be very trivial. The operator corresponding to position is x itself. So we have a set of operators, P operator, E operator and X operator. The E operator takes into account the dependence of T, and so if we have a classical expression, we can replace this the dynamical variable in the classical expression by the corresponding operators. But the operators should satisfy certain conditions. What are the conditions? If you look at this expression, this is the operator and this is the momentum that we generally obtain experimentally, and similarly this is the energy that we obtain experimentally, because any development of quantum theory must be considered from the experimental point of view. Because in quantum mechanics, performing and non-performing of experiment is very important. So whenever we want to speak something about quantum system, we must perform some measurement. So the theory is developed in this light, that whenever we may make some measurement on momentum, we get the value of momentum, which is P. And since an experiment can directly measure only real quantities, the PE, they are real, but we should ensure that the eigenvalues of the operator are real. We know the Hermitian operators which have real eigenvalues, so we may say that we have to replace the dynamical variables by the corresponding Hermitian operator. The question arises whether these operators are Hermitian. Yes, they are indeed Hermitian, as will be proved later on. For the time being, let us assume that they are Hermitian operator. Then what can I do? We know the only expression for free particle in 1D is the relation of its energy with the momentum. Now, for non-relativistic particle, m is a constant, so the dynamical variables are E and P. If we replace E by E operator, and this is 1 by 2m will be there, and P by P operator square. Operator square means the operator acting twice. If we write this is IH cross del T, and on the right we have P square operator. If we operate twice, this is H cross, and this is operating twice is my I square, which is minus. This is a differential operator. This will have meaning only when this operator operates on some function. Since there are partial derivatives with respect to x and t are involved, the function, the operand on which the operator operates must be a function of x and t. So somehow we have arrived at an equation which is a partial differential equation involving x and t, which may represent a free particle in one dimension. Before we can say it definitely if its solution leads to an equation of this sort. Now note that this equation is a linear equation. So the basic requirement that we put forward that the equation describing the wave packet must be linear. Yes, it indeed satisfies this condition. Now let me solve this equation by using the separation of variable technique. So our aim is to get back the solution. That is, at present what I have done, I have done this. Let me summarize what I have done. Here, for a very trivial case, we have taken a very trivial case and arrived at this result. That is, for a free particle, starting from a free particle by introducing the concepts of operators and etc., we have arrived at this equation. If starting from this we could arrive at this, then the theory will be a consistent one. So this has already been done. This is yet to be done. If this leads to the solution which is physically acceptable, then we may consider to be on the right track. We may consider that we are on the right track. So according to separation of variable technique, we write psi of xt as x of x and t of t, where capital X is a function of x only and capital T is a function of t only. Now we apply this on this equation and assume that the solution is non-trivial. That is, this is not zero always, so we can divide by whole side by both the sides by this, and the result is here we have used T dot is equal to x prime is equal to this the left hand side is a function of space only and the right hand side is a function of t only. So we equate it as separation constant. This is separation constant. The T equation becomes T dot is equal to alpha by IH cross T is equal to minus I alpha H cross T, or dt by capital T is equal to minus I alpha H cross dt, whose integration leads to T as a function e to the power T by H cross. You consider the temporal behavior of a wave. The temporal behavior of a wave is e to the power I omega t. So comparing these two, we get that alpha is equal to H cross omega, that is E, the energy of the particle. So the separation constant has a special significance, it is the energy of the system. Now what will be the space equation in that case? The space equation in that case is equal to I have made the mass simplification. So this is equal to E, so x is multiplied by E, so on the side it will be twice m e h line square x, and which is taken this will have sinusoidal solution, and the solution of x is e to the power plus minus I kx. Plus sign represents this plus sign represents a wave traveling towards the positive x-axis, and this represents a wave traveling along the negative x-axis. So from here we come to the solution that psi of xt is equal to a e to the power I kx omega t plus b e to the power minus I kx plus omega t. This represents a plane wave traveling along the positive x direction, and this represents a plane wave traveling along the negative x direction. We started with a free particle moving along x direction, so the particle may move with the passage of time. The particle may move towards the right, which is represented by this, and particle may as well move towards the left, which is represented by this. So the solution that we have obtained by solving this is physically acceptable, and it seems the prescription that we have opted for is good enough to represent the particle associated with the the wave associated with the particle. So this is also done, and we come to the situation that the solution of this leads to the solution, and this basically known as time independent Schrodinger equation, time independent Schrodinger equation for 1D free particle, for 1D free particle. What happens to the situation when the particle is subjected to a force field? When a particle is subject, we are confining ourselves to the one-dimensional case only. When a particle is subjected to force field, its energy expressed, the force may be a conservative. If conservative, can be represented in terms of potential, and it may be non-conservative, then there is no potential function exists. The general treatment of a motion of a particle under non-conservative force field is very tough even in classical domain. So for the time being, we are considering only the conservative force field. Conservative force field. So it is represented by a potential. So it is represented by a potential minus del V del x. And the energy expression for the such particle E is kinetic energy plus V potential energy. The expression for kinetic energy is known. It is p square by twice m for translational motion, and for rotational motion the thing will change. And the potential energy, since the potential force is conservative, the potential does not depend on time, so it is this. And this is the total energy of the particle. So what shall we do first? Starting with this, we replace this by its operator. So this is IH cross del psi del t I am not writing the okay, let me write the arguments, and from this minus h line square by twice m del 2 psi of xt del x2 plus v of x. Incoming from there, we did we have replaced the dynamical variables by their corresponding Hermitian operator, and the operator equation has been converted into a differential equation by introducing an operand. This is called a wave function. And this is known as time dependent Schrodinger equation in 1D under the action of a potential V and the mass of the particle is m. Now, depending on the values of V, we can solve this equation, but we need to have a definite solution. To constant of integration will appear, and we have to find out some prescription or the boundary condition so that this constant of integration can be evaluated. That will be taken care of by a next lecture. Now let me first generalize this one into more than one dimension. This is the and one thing more, if we decouple the space and time part into this is time dependent Schrodinger equation in 1D. If we decouple this into space part and time part, then we will time part will be same as we have done earlier. The time part is and for this E, the space part will be governed by this differential equation. In one dimension, we need not to write partial derivatives anymore because the decoupling has been done or accomplished. This may be looked upon as an eigenvalue equation where Hamiltonian it is an eigenvalue equation of the Hamiltonian operator. The Hamiltonian operator of a conservative system basically turns out to be the kinetic energy plus potential energy, and when the kinetic energy is replaced by kinetic energy operator and potential energy is replaced by potential operator, this is the classical expression, and in quantum mechanics this is T operator plus V operator, where T operator we have just introduced minus h line square by twice m del 2 del x2. And for potential operator, it will be dependent on the potential function. Say for for harmonic oscillator, the potential operator is this, and so since x operator is x, this is also the operator corresponding to potential. In 3D, come to 3D case. In 3D, let us consider the system be represented by Cartesian coordinates. So it is 3 directions will be there, x, y, z, and the operator corresponding to x momentum operator is now minus I cross del x. Similarly, the operator py operator will be, and z operator is so that the vector p operator is I cap px operator plus j cap py operator plus k cap pz operator. So this is combining these two, minus h cross nabla. This is the operator, the three-dimensional momentum operator. So for a particle of mass m, we under the action of a conservative force field, the Hamiltonian of the particle is T operator plus V operator. T operator is P vector operator operating twice by, it is a function of vector r and they are operators. So this is the corresponding Schrodinger equation, time dependent Schrodinger equation is minus h line square upon 2m. The wave function now depends on x, y, z and t. The x, y, z has been put in a compact form under vector r. This is time dependent Schrodinger equation in 3 dimensions, and if we decouple it into space and time part, as we can do always when the potential does not depend on time, the equation that is this is simply the eigenvalue equation of the Hamiltonian we have given. So this is the Schrodinger equation. We have come or arrived at Schrodinger equation for 1-dimensional and 3-dimensional particle under the action of a conservative force, or under the action or for free particles. Now the task remains to associate some physical meaning to this wave function, which will be taken care of in the next class.